life is that it's easy to make mistakes when writing. Humans are pretty good at filling in the blanks, so when we read a story, we can understand it even if it has typos or missing words, grammatical errors, and such. When you're writing instructions for a computer, you have to be very precise, and your grammar must be 100% correct. A happier fact of life is this: the easiest programming errors to make are syntax errors, and they're also the easiest ones to find and fix. It's easy to forget a comma or a square bracket, for example, but when you do, MATLAB will complain with one of those red error messages, and you can fix it. But semantic errors are more problematic. You'll remember that these happen when what you wrote is legal, but it doesn't do what you meant for it to do. Sometimes MATLAB can catch these semantic errors. For example, suppose you have a 10-element vector. You want the last element, but you ask for the value of the 11th one. MATLAB will stop you with an error message and you can fix your program. What if you ask for the last element when you meant to ask for the first one? Well, your program may run just fine every time and give the wrong answer every time. In cases like that, the results will usually be consistently suspicious, and you're likely to realize that something's wrong. Finding the source of the problems may be difficult, but knowing that there is a problem is a big step toward solving it. Some semantic errors may cause problems only occasionally, though. That typically happens when only a certain combination of inputs triggers the error. This is the hardest case of all. First off, you may not notice the problem, and second, it's hard to find the cause. For that reason, it's very important to test your program with a wide variety of inputs. In fact, you should think hard about the possible problem cases for your program, and you should test all the ones you can think of. If one of these cases causes an error, then you need to find it and correct it. Many times, however, finding it can be surprisingly difficult. Fortunately, MATLAB can help you with a tool called the debugger. The name bug is synonymous with error in computer programming. It comes from the early days of computers when an actual insect caused a problem in one of the first computers. The name stuck, and now any tool that helps you remove errors is called a debugger. So let's see MATLAB's debugger. And if we want to use the debugger, we got to have some bugs, to debug. So let's practice making some errors. Remember what happens when we do that? Well, let's start with a few intentional syntax errors to refresh our memory. Wow, that's a lot of red text, but it should be familiar red text. We made this same mistake in Lesson 1 when we first introduced the concept of syntax and syntax errors. And naturally, we saw the same exact error message. MATLAB is nothing if not predictable. It's telling us that we messed up the assignment. Of course, you know by now that it should have been x equals 1 and not the other way around. So how about this error? A little less red here. Undefined function RAMD. Again, MATLAB is not shy about telling us that we fouled up. It can't find a function named RAMD because we didn't make a function named RAMD, and it knows darn well it didn't make one. So of course we got our hands slapped. Well, hey, we just misspelled RAND. Aren't you smart enough to figure that out, MATLAB? As a matter of fact, sometimes it is smart enough. For instance, suppose we just typed an extra D in the name. MATLAB yells at us in red, and then quickly calms down and politely asks us in black if we meant RAND. Well, yes, thank you. That's exactly what we meant. And all we have to do is hit return, and the function that it guessed we want runs. Let's make an error that's a bit more serious. Okay, we've got Y. Let's look at the 6th element. What happened here? Well, we created a 5-element vector and then tried to access its 6th element. There's no such thing, so MATLAB let us know. It's important to realize that this was not a syntax error like the previous ones. Y of x is a perfectly legal MATLAB expression. But when MATLAB tried to execute it, it realized that in the given context, it was illegal from a semantic point of view. This is called a runtime error, because MATLAB can catch it only when it tries to execute it. We should be happy when we see this red stuff, even though I'm usually not, because it means that an error that we made was caught before it could do any serious damage to the output or, to people who depend on that output. MATLAB spotted a bug, and once we know where it is, we can eliminate it. Sometimes MATLAB is happy most of the time when we run our program, but on some input combinations, it runs into a runtime error. We may be thinking our program is perfect and everything is rosy, and then out of the blue, MATLAB hits us with an error message. That's always discouraging, but again, we can be thankful that it caught a problem. Unfortunately, though, as we've pointed out before, many bugs are such that MATLAB will never know that there's an error. It simply executes the statements we provided and gives us the wrong answer. The best we can hope for in that situation is that perhaps we can tell that the result is not what we expected. Then we need to figure out where we messed up. Both of these latter errors can be very hard to find, and if we don't find them, we're doomed to failure. And that's when the debugger can be our only hope of salvation. That may sound overblown. It's not. Let's consider this simple function. It roughly mimics the behavior of the built-in Randy function. In fact, it uses Randy, as you can see here. It's supposed to return an n by m matrix of random integers, right here in X, and print out the last number on the last row. It uses fprintf to do that. The last number on the last row, since it's an n by n matrix, that's element n by n. Yeah, that looks right. Well, let's try it. Now it looks pretty good. It's 3 by 3. They look random. Last element on the last row is 3. The only thing I'm noticing here is that we only get integers 3 and smaller. Wonder why that is. Let's try it with a different input. Well, we're in trouble right there. Index exceeds matrix dimensions. Error in rand int line 3 fprintf. So, by the way, the first thing to notice is that these are live links. If I click on this line 3, it takes me to line 3. Well, what do you need that for? I mean, it's obvious these lines are numbered here. Well, the advantage of that is if you have a really long function, then it'll take you right to that point and you don't have to scroll around. When I'm looking at it, I know the error is here. I know I've got an n by m matrix. How can this not be legal? How am I exceeding? It'd be nice to see what the size of x is. It was 3 by 3, right? But there's no x here because the workspace doesn't have the local variables in it, just has the variables in the command window. Well, I'm at a loss. It's time to use the debugger. The most important feature of any debugger is the ability to put breakpoints in your program. You use a breakpoint to mark a line in your code that you want the debugger to stop executing the code at. It's called a breakpoint because it breaks the flow of execution at a chosen point. To create a breakpoint, you simply click in the gray area between the line number and the given line on one of these dashes. Let's do that on line 3. The red circle indicates the location of the breakpoint. It's sort of like a red stop sign. We're going to stop right there. It'll stop before this line is executed. And we want that because that's where the error was. And you can have more than one breakpoint. You can have one on any line where there's a dash, on line 2, for instance. There. I think that might be a better place to stop, so let's get rid of the one on line 3. We don't need that one. To remove it, simply click on the red circle. It's gone. Okay, let's go back to the command window and call our function again. Call it the same way we did last time. The function begins to run, then it stops. And there's this little green arrow next to our breakpoint. What happened is that the debugger paused the execution of our function just as the code pointed out by the green arrow was about to be executed. Now we have several options. We could simply continue running the function by clicking the Continue button up here on the toolbar, or by hitting the F5 key on the keyboard. Instead, let's execute just the current statement by clicking the Step button right here, or you can do that by hitting the F10 button. So I'm going to click that and watch the arrow advance. There. And something happened over here. X showed up. Wait a minute, M, N, and X. These are local variables. We've never seen local variables in a workspace. Well, this is a great thing about the debugger. When you're stopped inside the function, the workspace that's shown over here is not the command window workspace, but the workspace of the function that's active. This is the workspace of randint. These are the local variables in randint. Let's see. Now that we're looking at this, X is not a 3x2 matrix at all. It's a 2x2 matrix. So wait a minute. We just gave it 3 and 2. Oh, and note the handy little yellow windows that the debugger pops up to show us the value of variables that we hover the mouse over. And we know that Randy makes a 3x2 matrix in that case. Doesn't it? Okay, maybe it's time to look at how Randy works. We can do that with a help function. But before we do that, notice this blue 2 down here in the command window. That number and X equals Randy of N, comma, M told us the line at which the function was stopped by the break and the code on that line. The blue color in the underline right here mean that this is a live link that will take us to that line when we click on it. And more importantly, notice that the prompt has a K before the 2 greater than signs. That K means that you can do things with the keyboard while the function is active. Yes, the function's active, but we're controlling it. It's like a person in a hypnotic trance who does what we tell it to do. Ordinarily, while a function is running, you can't communicate through the keyboard with it, or with MATLAB in general. But you wouldn't realize that because the function is over so fast. You will realize it, though, if you have a function that runs long enough to give you a chance to hit a few keys before it returns. When you do that, you'll see the characters that you type in the command window down here, but they'll be ignored, except for one magic combination. You remember what that is? That's the magic combination that will stop the function cold. It's Control-C. Everything else will be ignored. Anyway, this K always appears in the prompt when the function is stopped at a breakpoint. And when it's there, we can use the keyboard to make things happen. For example, we can look at the value of one of the variables in the function's workspace. Let's look at, say M. Well, we knew its value was 2, but it's fun to look at it. You know what's more fun? You can change it. Let's make it pi. Now M is equal to pi, and I want to emphasize that I'm talking about the M in randint. The input argument that was set to 2 when the function was called has been changed to pi. And look over here, there it is, pi. Remember, this is the workspace of the active function here. Of course, if we continue this function by hitting, say, the Continue button or the Step button, pi is the value that'll be used right here inside fprintf when it's executed, and we'll get a new error saying that an index has to be a positive integer. That would be no help, but peeking at variables like this or changing them can sometimes help you figure out what the problem is. For example, if we'd have looked at x, we'd have seen that it's 2 by 2 instead of 3 by 2 as we expected it to be. We already saw that in the workspace window, but it's more obvious now. Okay, let's refocus here. We were going to get help on Randy. Let's do that. Let's scroll up to the beginning. There. Randy, pseudo-random integers from a uniform discrete distribution. R equals Randy, I max, comma, n, returns an n by n matrix. There's the problem right there. The arguments aren't the size of the matrix. Like what do we put? 3 by 2. That means the maximum value is a 3, that's what we saw, and the matrix is 2 by 2, which is what we saw. There it is, maximum value 3. Okay, there's our problem. We didn't know what Randy was doing. Okay, let's fix our little broken function. First, we need to quit the debugger. We can quit it either by typing db quit, that's for debugger quit, or by clicking the Quit Debugging button up here. It's the red thing. I'm going to click that button. And watch the green arrow when I click it. Okay, 4, 3, 2, 1, click. There. Green arrow disappears. And down in the command window, we've got our normal prompt back. You know, the one with no K. Now here's how we're going to fix our function. We're going to change x equals Randy of nm to x equals Randy of 10 nm. Note that this breakpoint turned gray when I did that. This is MATLAB's way of indicating that the breakpoints are inactive and you need to save your function before running it again. They'll all turn gray whenever you change the file, and they'll only turn back red when you save the file and it's got no syntax errors in it. Well, I don't think there's a syntax error here, so I'm going to click the little blue diskette over here to save the file right here, and you'll see the breakpoint turn red again. Here we go. There. Well, I can almost hear you complaining about the way we fix this function, because the change we made will mean that we've arbitrarily limited the range of pseudo-integers to go to 10. Good point. We can think about whether that's a serious problem, and if it is, how we might fix it. But in the meantime, let's just call that a feature of our function. Okay, ready to see whether it works now? Well, we'll leave that up to you. Try it. Try it with several different inputs. If it is working, then we can say, "Thank you, debugger." If it's not working, then you'll know how to find the bug and fix it. And then you can thank the debugger. As you might guess, MATLAB has extensive documentation on its debugger. You can get a good start on that by typing debugging into the little query box here. And then coming down here and choosing Debugging Diagnose Problems with MATLAB Programs. And you get lots of information right here, examples, and so on. Well, that's it for the debugger for now. But when we start writing more complicated programs in later lessons, more bugs will inevitably appear in our code, and you'll have more chances to practice with a debugger. And as you write more and more code, you'll get more and more practice, more than you might expect. And that brings us to today's message about life as a programmer. After you finish this course and begin to write more sophisticated programs on your own or with collaborators, whether it be for fun, for another course, or for your employer, you'll find that most of the time you spend on programming is debugging time. In fact, it's worse than that. Only a small fraction of programming time is spent typing what we think is correct code. The great majority of time is spent finding and removing the errors that we made while we were typing what we thought was correct code. And now for the most important part of the message. Programming is a very humbling experience. It shows us, as well as any exercise I've ever seen, just how imperfect we humans are. Wait, did I say humbling experience? Make that humiliating experience. And it can be very discouraging too. In fact, if you don't get discouraged, then either A, you aren't writing serious programs, or B, you aren't human. If you are human, and you can endure the humiliation of making 99 errors before you get one thing right, then you should make a good programmer. And you won't have many competitors, because most people will give up after a mere 10 errors. I'm convinced that this single factor is the reason that programmers are paid so much money. Everyone else gets discouraged and quits. But hang in there, because programming is also an exhilarating experience. When you finally get a big program working, and it works its way through inputs that it's never seen before, making decisions and doing calculations that would take 1,000 people 1,000 years to do, and when it carries out all those billions of calculations flawlessly and spits out the answers, you'll forget all the hours of humiliation that preceded it. And when you get there, it's a feeling that is amazingly wonderful. Well, you just have to experience it for yourself to know what I'm talking about. If you do, then this course was worthwhile. But frankly, most of the credit must go to, well, can you guess? Right. Thank you, Debugger. And with that thank you, we'll end Lesson 4.